Okay, so continuing, and sorry that the first part got dumped, but problem 26 is going to be an example of working with independent events. So let me flip over there, let you read the whole problem. So you got hospital generators. Um, Hospitals typically require backup generators to provide electricity in the event of a power outage. Assume that emergency backup generators fail 22% of the time. How many people lost power last March during those big windstorms? Just a couple of us? Man, the rest of you guys are lucky. I was out for like 5 days. I would not buy a generator that failed 22% of the time. That seems outrageously high. Now, your author is really careful about his research. I mean, this is based on data from the Arshad Mansour, Senior Vice President with the Electrical Power Research Institute. 22% of the time? Sounds like an awful lot. So a hospital has two backup generators so that power is available if one of them fails during a power outage. Find the probability that both power generators fail during a power outage. So that's where we're at with problem number 26. Find the probability that both of them fail. There, that looks better. Let me denote the event of a failure with an F. Event, a generator fails. If I want to find the probability that both of them fail, it's going to look like this. Probability of F1 and F2. I'll try and be explicit about some of these things on an exam, but let's assume that the probability of these generators working are independent of each other. So assume independence. So if we can assume that they're independent, then this probability becomes a little bit easier. It's going to be the probability that the first one fails times the probability that the second one fails. Christopher, what's the probability that the first one fails? Yeah, 22 over 100. Let me just write it as 0.22. And the probability that the second one fails? Tyler? 22 again, right? 0.22 times 0.22. So you're going to have to help me out because I was never very good at math. 0.0484, I think. All right. Now, that's part A. Part B is kind of nice because it asks you to use a little bit of thought. Find the probability that the hospital has a working generator during a power outage. So that means one could work, the other could work, or they both could work. Well, I'd rather not try and calculate three different possibilities. I'd rather deal with one. If you take a look at what's going on, kind of a grid, they both could work. The first one could fail, the second one could work. The first one could work, the second one could fail, or they both could fail. So those are the four different things that can happen with our generator. If you're to try and figure out the probability that at least one works, that would be any of these three, right? They both could work, one could work, the other could work, etc. But that means calculating three probabilities. What I'll do instead is I'll use the complementation rule. The probability that at least one works, what's the opposite of at least one works? Yeah, they both fail. It's going to be 1 minus the probability that they both fail. And you can see that here. The only thing I didn't circle was this little piece in the bottom right-hand corner. Probability that they both fail. I don't want to, let's see. Let's do it with this color. So 1 minus the probability that they both fail. 1 minus 0.0484. So 0.9516. There we go. So the author in this problem and the next problem seems to be expressing a little social conscience, it seems to me. This is the probability that you're going to have power during a power outage. Is that probability high enough? Yes? If you're on life support, is it okay to have only a 95.16% chance, or are you going to want that to be a little bit higher? Yeah, I'm thinking that it might be nice to have a 99% chance or something a little higher. Yes, sir.
I did it a different way. I did it longer.
Okay.
So I did it with all three, the probabilities that you put. So I put 78 over 100, then 156 over 200 times 78 over 100. Could that work?
To do this the long way would really be the long way. Let me. Well, well, let me. Well, let me show you how. If you wanted to do it the long way, we'd have to do all three of these. So it'd be probability of W1 and W2, or W1 and F2, or let's see which one. I mean F1 and W2. So there'd be a lot of different things you'd have to consider. The nice thing about these things is that they're mutually exclusive. You'd have to just add up the probability of all three of these events. So what would that be? It'd be the probability of W1 and W2 plus probability of W1 and F2 plus the probability of F1 and W2. I'm thinking you might not want to do it this way on an exam. So this is the probability of W1 times W2. There's a 78% chance that they're both working. Plus probability, and I'm not going to write all of it. It's getting a little bit long as it is. Plus this probability. And then this last one would be 0.22 times 0.78. So theoretically, that should add up to exactly what we got.
Okay.
And if you did that, yeah, I'd give you credit, sure. But I'm thinking most people would probably want to do it the other way. Yeah, but yeah. Did you do it this way? Did you get these numbers? Just out of curiosity.
Yeah. I looked at the question a different way than you. That's what I was thinking. But like on an exam, I'm not going to be able to ask you like how to do it. So,
This is true.
yeah. Make sure I did it.
Or you could ask, but you might get kind of a blank stare back. All right. Well, thank you for that. Anything else on 26? Yeah, I'll always look at your work. You don't necessarily have to do it exactly the way I did it. And if you're creative enough to come up with something like this, yeah, sure, I'll mark it right. No problem. Let's look at problem 28. And again, I've kind of abbreviated things a little bit for us. I've got this abbreviation of NOAA. Now, this is the governmental agency that inspects your seafood. Does anyone know what NOAA stands for? They inspect your seafood. It's National Oceanic and Atmospheric Administration, which sounds like a funny place to put seafood inspection, but it is what it is. So we're going to assume that we have a lot of 2,875 containers. 288 of these do not meet requirements. So it has to be certain purity requirements, and they're not met. Now the way that NOAA would inspect this kind of stuff is they're just going to take a small sample and test that small sample. If all of those samples pass, then great. Then the whole lot is passed. If one of them fails or more than one of them fails, then they reject the whole lot. So it's an all or nothing thing. So let's let M be the event that a container meets the requirement. Container meets the requirement. We're going to test 3 containers, and for the entire lot to be accepted, what has to happen with all 3 of those containers? They all have to pass, right? All of them have to pass in order for the lot to be accepted. So let's write it this way. Probability of being accepted would mean probability that the first one meets the requirements, and the second one meets the requirements, and the third one meets the requirements. All three of these. Are we sampling with replacement here? No. You wouldn't want to bother sampling one twice. That'd be silly. Although we will look at that in a minute. But for now, let's work on sampling these without replacement. So 2,875 containers, 288 of these do not meet the requirements. So which proportion of these, or what number of these, actually satisfy the requirements then? 2587 minus the 288. Yeah, so, or 2875 minus the 288, 2587. Just what you said, thank you. 2587 over 2875. So that's the probability that the first one meets the requirements. Now you look at that one and say, hey, great, it meets the requirements. All right, on to the next one. What's the probability that the next one meets the requirements, given that you've already taken out one of them that does meet the requirements? Thank you. 2586 over 2874. Cool. And one more. What's the last one? Andrew? Perfect. Thank you. So let's calculate that probability then. So what I'll do is I'll multiply 2587 times 2586 times 2585 divided by, now when you do the divided by, we got to divide by this whole thing. So we got to be careful. We want to put that denominator in parentheses. Divided by 2875 times 2874 times 2873. So I'm getting 0.7285, approximately speaking. You guys getting the same thing? Okay, good. So again, here's your author's social conscience. Does that probability seem adequate? So there's a 73% chance that this batch would get passed. And that batch has 10% of the containers don't meet requirements. So that means if this batch got passed, 1 out of 10 times when you buy this fish, you're getting something that doesn't meet requirements. So is this enough of a sample to ensure your safety? I don't know. So again, I think the author's trying to make a little point here. He targets one of the airlines too at some point. I can't remember which one. It's like, take a look at their on-time rating. So, all right. Our goal, our concern, of course, is the calculation of this part right here. Finding the probability that the batch would be accepted or not. What's the probability it would be rejected? Yeah, 1 minus this. So about a 27.15% chance of it being rejected. So about 1 time out of 4, a batch like this would be rejected. So not that often, really. Let's continue with this a little further. So on the flip side of your handout, or the next page, what if we redid this and said, all right, you know what? Let's assume that for whatever strange reason that you're going to sample something and put it back, mix it up, and resample. How is that going to affect our probabilities here? Well, let's see. We're still going to calculate the probability of M1 and M2 and M3, M1 and M2 and M3. Now the first probability is not going to change in any case. So it's just going to be 2587 over 2875. But after you take the first sample out, you look at it, you put it back in, you shuffle the deck, and you take a second sample out. What's the probability that the next one meets the requirements? Same as the first one, right? And then for the last one, same thing. 2587, 2875. In other words, it's just this to the third power. 2587, 2875. Which one's an easier calculation for us on our calculators? This one, right? Because all you have to do is put in one number. In fact, here's kind of a nice little trick that you can do. Let's calculate the first one, 2587 divided by 2875. So I've got that one. Hit the up arrow key that you use for exponents and raise that to the third power. There you go. Did it make much of a difference calculating it this way? We get the percentage of about 0.7286. Is this much different than what we calculated the first time? No. So we're going to have kind of a little fudge rule for ourselves. Since it doesn't make a huge difference which way we calculated it in certain circumstances, we're going to take the easy route. It's called the 5% rule. It's something that your author tends to like. So I get used to it, comfortable with it. Basically, it says if your sample size is no more than 5% of the population, you can treat these as being independent. In other words, you just calculate that first probability and then raise it to the appropriate power. Because look, it didn't make that much of a difference. If you compare that to 0.7285 from our previous calculation, they're pretty close. So let's apply that rule to the next problem, problem number 30. Before I get to problem number 30, are we okay with the second part here? Good on that part? Nick? Okay. $47,637 patients are transported by helicopter. 188 of them leave your treatment center against the medical advice. The rest of them, so this minus your 188 gives you 47,497 who did not leave against medical advice. So some leave, some don't. Most of them don't. If 40 patients of the subjects transported by helicopter are randomly selected without replacement, what's the probability that none of them left the treatment center against medical advice? So let's say S is the event that a person stayed. They did not leave the treatment center against medical advice. All right. What are they asking us here? They're asking us for the probability that 40 of these subjects, randomly selected, all of them stayed. So if you're looking at it in terms of probability, it'd be the probability the first one stayed and the second one stayed, all the way down to the 40th one. Wow. This could be a real pain if we had to do it the long way. But let's keep something in mind here. You're sampling 40 patients out of a pool of 47,449. Now, I don't think I need my calculator to tell me that that's less than 0.05, but let's actually calculate it out. It should be less than 0.1, I'm guessing. 47449. So it's 0.000, so 3 zeros, because this is in scientific notation, 84. Yes, sir.
Question. Why did we not use the 47,637 total patients?
I should have. Thank you. Yeah. Although it's not going to make a big difference. Yeah. 47,637. Yeah, good question. I should have. Yeah, it's still going to be less than 5%. So I just absentmindedly grabbed the wrong one. But thank you. So it's going to be about the same point. You got me curious now here. Sorry. It's identical. All right. 0.00084. The bottom line is that they're both less than 0.05, which is your 5% rule. What that allows us to do is treat this as if that they're independent. Probability of S1 times probability of S2 all the way down to 40. Now let's just start with the first one. What's the probability that somebody stayed in accordance with the medical advice? Well, 47,449, 449, divided by 47,637. How about the second person? It's going to be the same. We're assuming they're going to be the same, even though it's different by a little bit. You'd have to subtract one from the numerator and denominator, but it's really not going to make a meaningful difference. So we're going to get this to the 40th power. Now let's see what that probability is going to end up being. 47,449 divided by 47,637. So virtually everybody is staying. And if I raise that to the 40th power, so hit that little up arrow key right above the division key, raise it to the 40th power, I get my probability. So about 0.8537 or 85.37% chance that all 40 would stay. It's a nice simplifying assumption. Without that assumption, do you realize what this probability would look like? You'd have to do this. You'd have to subtract 1, so you'd have 47,448 divided by 47,636, and then keep on subtracting 1 for 38 more times, and then multiply all those things together. No thanks. I'll do it on a spreadsheet. I'm not going to do it by hand on a calculator. Even on a spreadsheet, it's a little annoying. Not too bad. Okay. How are we looking on this one? Looking okay? Are you comfortable with the 5% rule? To see the convenience of the 5% rule. Because I'd really hate to have to do this the long way. It would be a bummer. Okay. For homework, let's see where my book go. My book's gone. Someone borrow a book. Thank you. For homework, try 1 through 29. Odds. This is section 4.2.